of the four of us, I think I'm the one who likes Phaseplot the most. I'm gonna take that mantle. So I got to be the person who walks us through Phaseplot. And the other thing is I'm probably the one who has definitely the one who has developed in YT the least. So this is going to be a little bit more of like a user-based walkthrough rather than a developer walkthrough. But luckily they're all on the call so they can answer any developer type questions we have. So, right. So I'm going to import YT and NumPy, and I don't even know why I import sys at this point. I think that's a holdover from an older code. And then for me, I was going to have us bounce around and define new fields, new derived fields kind of while we went through the notebook. But for whatever reason, I was having to rerun the entire kernel every time I added a new derived field. And so I'm just going to throw them in all at the top here, and we'll touch on them later. And so we've talked a little bit about derived fields. I think Matt did dinosaurs yesterday. Mine are slightly more physical. I have this metal fraction, which is just the metal density over density. And I think I could have called metallicity, but it wasn't doing exactly what I wanted here. And then I did z new, which is this coordinate that's going to tell me the distance from the center of the galaxy, or from the z coordinate of the galaxy center, which I have kind of insider knowledge is at 0.53 in the z coordinate. And then I also did the same thing, but I took the absolute value. Okay. So now I'm going to run this, and I'm going to load the data. And this one is slightly different than isolated galaxy. This is high res isolated galaxy, or maybe it's just high res galaxy. It looks like people are chatting on Slack, but I can't read them without everyone reading them. So I'm going to just totally ignore that. So if anyone's asking me a question on Slack, do it on Zoom. Okay. Right. So if we wanted to understand what variables were in our data set, we could look here for our fields. In ds.fields.gas, we could print our fields. I'm not going to do that because it's really long, and we've done that a couple times with other data sets. And I've loaded my data, so now I can add my variables as new fields. And so I'll do that. Okay, so now I have these nice new fields, yep, which is fine. I think because metal fraction, met F here that I've defined, is unitless, because it's a density over a density, it didn't scream at me about defining units. The other two, it did kind of yell at me, so I had to actually call in the units, just to kind of walk you through what was going on. Okay, so let's take a look at what we've got here. So we're using kind of just the plain old projection plot. We're going to look at the entire domain. We're just going to look at a density projection along the x-axis. Okay, so we have this nice little disky galaxy. Looks much more galaxy-y than isolated galaxy to me. I don't know if Mike's galaxy class would agree, or if this is too just guts. Galaxy
My
guts.
galaxy class mentioned the word galaxy 4 times in the whole semester.
Okay, awesome. Well, then that's probably very much like a galaxy from his galaxy class. Okay, so, all right, great. So it looks like this galaxy is centered. Yeah, just from eyeing this, it looks like it's at 0.53, 0.53, 0.53, or, you know, maybe it tells you that when you download this. And then, so the things that I care about when I'm looking at galaxies is I care about, you know, what gas of different densities is doing kind of in the disk. And so this is a really big domain, and really all I care about is the disk. So I'm going to select that region. And I think I get to be the first person to have selected a disk region, which is pretty exciting. Oh yeah, sorry, Keaton. I think that you can, if you have downloaded this data set, you can do this yt.load. But if you haven't, then you can do, I think it's load sample high res something. I don't know if anybody can help me out.
Isolated galaxy.
Yes. Yeah. Yeah. And so that should work for you to do that on your own. Okay. Right, because load sample is new to YT4, which is extremely cool. Okay, so okay, so I get to be the first person to select a disk. Here's my center, 0.53, 0.53, 0.53, which is the center of the disk. I set a angular momentum vector, 0, 0, 1. My radius is 50 kiloparsecs. And then my height setting is 5 kiloparsecs. So yeah, so each of the kind of regions that you can select have slightly different directions for how to do that, but this is pretty similar to, I think, what you've seen for the other regions. So, okay, so I'm going to select this region. If I had wanted, I could have selected kind of a similar region using ds.box, which then I would just kind of give it the corners to select a region surrounding the disk. Okay, so now let's take another look. And for whatever reason here, I decided that I wanted to look at a slice plot. So I can do that. And now you notice, so I've got DS is kind of my whole data set, Z slice of density, and then here I've set my data source to be disk U, which is disk U's. Very clever. And that's what I've set to be my disk region. Okay, and I'm centering my slice. I don't know that I actually had to set this. And then you can set the width of your slice panel here. If I didn't set this width, I would still just be taking that disk selected region, but I'd have like a whole lot of white space around it. You can kind of get an idea of that here. So because I've selected a disk, I have this circle here in the slice space, and I have white space out here where I don't have any data. And so here's a nice density projection. Ooh, I don't know. I feel like that looks super disky to me. So I like this one. Okay, and here we can look at a projection, which is just going to be all the data rather than just a slice through the data. And if we run that, get here. So this is, I think, a repeat of stuff that we've already done, but for me anyway, I find that to be pretty useful to kind of repeat, especially since we're looking at a new data set. Okay, and so here's a projection, again, of projected density. Notice that I'm just doing that integral that Mike talked about, so it's grams per centimeter squared. And then the other thing actually that I thought was worth looking at is, so here I've got my slice, so that you're seeing this nice circle with the radius of 50 kiloparsecs, which is how I set my, I keep on pointing at my screen like you guys are gonna see my finger, which is what I set here when I set my region. But here, so here's kind of a funky thing about disks, which drove me mad until I just, decided to chill out. So here, if I do a slice plot in the X direction instead, here. Okay, so I've set my width to be 100 kiloparsecs. And so here you have this nice example where I have all this white space because in the width of this slice plot, I have no data there because I selected my height to just be 5 kiloparsecs. But notice that the height is not actually 5 kiloparsecs of this slice. So here's just like a little thing. Maybe it's been added to the docs. I don't know. It's actually 5 kiloparsecs up and 5 kiloparsecs down. So little fun fact about the ds.disk selection there. Yeah, so then when I look at this from the side, I can see, yeah, my 5 kiloparsecs is definitely mostly selecting the disk. I might have some excess, not disk gas, kind of above and below and to the sides. So, okay. So it's always worth kind of doing a few selections of your region. So I like to compare kind of my disk region to like a box region to make sure I'm getting similar gas. Okay, so we can look at the density temperature distribution of this gas to actually see like, all right, what kind of gas am I really looking at here? And in terms of the density and temperature distribution. And so I'm doing a phase plot, which is very much like a 2D histogram. I'm calling disk U, which is that selected region, that selected disk region. On the x-axis, I have density. On the y-axis, I have temperature. I am going to show in each bin the amount of cell mass in each kind of cell of density and temperature. And I have no weight field. So it's going to be the total cell mass in each one of these histogram cells. Okay. So, all right, this always takes a moment. And another kind of interesting thing about phase plot, which may or may not have an answer, anybody can jump in, is phase plot requires a region to be put into it. By that, I mean, I can't just do phase plot this line. This line will not work. Phase plot DS, density, temperature, cell mass, weight field, none, will not work. I have to do a region. Even if my region is just this DD all data, then my phase plot's okay. But phase plot will choke if you just give it the DS, unlike the slice plot and projection plot. I don't know why. So there's just a user fun fact. Okay, so if I look at this, this is just like a little bigger than I wanted it to be. But I have my range of temperature on the y-axis, just as I called it, my range of density on the x-axis, just like in the call. And then for each one of these little cells, I have the total mass in that entire selected region, disk U. But here's another funky thing, which may just be for phase plot, but I think it's also for slice plot and projection plot. If you have a really broad range of cell mass or maybe anything in the color plot, sometimes phase plot won't actually label these axes. And so you have to force it to label them. So I think it's like a magic number of like 8 orders of magnitude, or maybe it's 9 orders of magnitude, not totally sure. Yuan Li is the first person who pointed this out to me. So right now I have this very beautiful color range, but actually no labels here. So we can do a very similar command to what you do with any of your slice plot or projection plots. And we're just going to set the zlim. You always have to tell it what your z variable is, even though you've already told it there. And then I just set my ranges. Nice CGS units, which is my favorite. Okay, and then it's going to work. Okay, beautiful. And actually I guessed, well, maybe I didn't guess, maybe I did it a few times before I came on here, but now my range looks pretty good. I have a very similar kind of color range across here, and I have values on my cell mass axis, which is, you know, much more helpful than not. So here it is without. So my range is probably going from 10 to the 33 to, about 10 to the 42 in grams. So, okay. So one of the things that I fiddle with a lot are also kind of cut regions. And so as I showed you back up here on this slice, I said, okay, look, my disc region that I selected seems to be selecting a lot of this kind of like nice narrow disc. And maybe I care about this gas here, and maybe I care about this gas, but there's a lot of gas in my disc U region that is not actually disc gas. And so if I really want to focus in on the disc gas, maybe I want to try to do another selection. And so when I do that, I do another phase plot. And for that, I'm going to look at this metallicity fraction to see if, star particles are like dumping metals into my disk, or sometimes you can use metallicity as a tracer. Like I have high metallicity in my disk, low metallicity outside of my disk. That's often what I do. And let's see what we look like. And when we do that, again, I'm using disk U as my selected region. Y-axis is this variable that I defined, metallicity fraction. Then y-axis is temperature. And again, I'm doing cell mass. Weight field is none, so I'm just summing up all those fields. Okay. And you can see kind of a funky distribution here. So I have a lot of gas, kind of, well, again, I have no units, so that's super annoying. We could have set that, but in any case, I have some gas here between 10 to the 6 and 10 to the 7 Kelvin at very, very low metal fractions. And then I have this significant component of gas here at this 10 to the minus, or 1.5 times 10 to the minus 2 fraction, or maybe solar metallicity. Maybe it's 0.01295 if I had to guess. Anyway, so maybe I can get rid of a lot of the surrounding hot, low metallicity gas and make another phase plot where I'm only looking at the gas. So you could also take, if you wanted, you could do a slice. You can do that on your own time to kind of see what the metallicity looks like. And, oh, I think I messed that up. Let me fix this. I want this to be net F. So I feel like I can pretty safely get rid of all of the gas with a metallicity, with a metallicity fraction less than 0.002. Okay, so instead what I'm going to do is I'm going to do this cut region, which I love chaining cut regions and doing I'm mad about cut regions. So I'm happy that I got to show you one here. And so here I'm going to do disk choose, and I'm going to cut out from my disk U volumetric region, a region where I require all of that met F variable that I defined to be greater than 0.002. Okay, and I'll do that. And you could have probably extremely easily gotten rid of basically the same gas, right? If you'd done like a temperature cut and said, I want everything below 10 to the 6, you're getting pretty similar. Okay, so now let's take a look at our more finely selected gas. So we're doing exactly the same phase plot and same Z limits. Instead of using disk U, I'm using disk choose. And let's see. Okay, it's thinking about it. And okay, good. And it has a really similar shape, so it may not have mattered all that much that I got rid of it, but I actually did get rid of some gas here. If we scroll back up, I have a little bit more of a peak here in this range than I do now when I have that selection. So you can fiddle with those sorts of selections to your heart's content. Okay, but this is a ridiculous range in cell mass. Okay, so I'm saying that in one of these bins, this dark color here has a total mass of less than a solar mass, which is very, very tiny. Whereas, here I've got 10 to the 9 solar masses. So I don't care about all that low density stuff. I feel like, it's kind of drawing my eye to these regions where there's basically no gas. So I want to get rid of that in my phase plot. And so the first kind of obvious thing that I've done is I say, okay, well, I want to get rid of that. I only want to look at things that are, close to 1,000 solar masses. So let's just set my limits to that range. And then if I rerun this, then we can twiddle our fingers for a little bit and see what Phaseplots does for us. Okay, so it definitely set my bottom value to be 10 to the 36, but it's still showing me all of those temperature and density cells. And so this is not what I was going for at all. And, and it's, less helpful, I think, than actually just showing the full range. So instead, if you want to do this, you actually can jump right into your histogram and make a change within your histogram. And so for that, you want to use create profile. And so here I'm calling create profile. Why did I do it? I have two very, very similar choices. Oh, no, okay. So in any case, I can do create profile. Here I have disk U, it doesn't actually matter. I can change that to disk choose. And I'm creating a profile using density and temperature, and cell mass. This looks extremely similar to how I was calling phase plot. And here I'm setting the number of bins in each direction to be 128. And again, I'm setting no weight field. And then I can create this histogram from the profile that I just created. And I'm creating a histogram of cell mass. Now that I have a histogram, I can actually say, okay, now in each one of those cells, if you had a mass below 10 to the 36, I'm going to actually set that cell value to 0. And that's where I can start to really clean things up. And so now I do a phase plot from my profile, which I called profile, and I'll set my limits to 10 to the 36 and 10 to the 42 like before. So a lot of what I do actually is using these create profile instances so that you can have your histogram look exactly how you like. And now you can see that when I set those values to 0, now I really am just showing you cells where I have at least 10 to the 36 grams at some temperature and density. Okay, so now I feel like I've selected the right gas to look at, so that I'm just looking at my disk. And maybe I want to look at, the rotation of gas in the disk. And so again, I have my phase plot. I'm using my disk choose, where I hopefully have just selected gas that's associated with the disk. I'm looking at its cylindrical R because I'm in a disk, and the velocity cylindrical theta. Again, cell mass, weight field none. And I can set my Z limit just like I do in the other plots, my units. I can say I really don't want log units. It looks kind of bizarre to me to have radius and velocity in log units. And then I can run it and see if I get a nice rotation curve for this galaxy. just going to run the next one too, so maybe we don't have to wait quite as long. And I think maybe Matt can verify for me on this. I don't know how this would work if I was not using a disk region. Like how would velocity cylindrical theta be set if I wasn't using a disk region?
I think it would throw an error, that it would
Yeah.
require you specify a normal vector so that it knew the angle of the disk.
Right. Okay. Yeah. So this is working because I already have that disk region chosen. Great. And this is going slower than I remember. But give it another minute. Okay, there we go. All right, so now I have this nice rotation curve. For those of you who can't remember Galaxy class, this is a nice, pretty nice rotation curve. It's relatively flat out to a pretty large radius, going out 40 kiloparsecs here. But there is a little bit of a spread here. This is in 10 to the 7th, so hundreds of kilometers per second. So it's like a Milky Way-ish, maybe a little bit more massive galaxy. But there is a big range at any radius of my cylindrical theta. And so I can say, okay, well, let's figure this out. And so now, instead of just plotting the cell mass and summing that up, instead, I can say, okay, well, I want my values colored by density, and I want the average density of any gas that falls within this cylindrical radius and velocity bin. So I use weight-filled ones. And again, I'm setting my units and log. I don't know if this would carry over from one plot. No, I don't think it would, because I have this plot.setLog. And then I can take a look and see if this gives me any extra information. And we can see if it does. And I'm just going to run the rest of them so that we don't have to sit around too much, maybe. Yeah. Okay. So, I feel like this is so beautiful. Like, look at that. My high density gas, I have this very nice density profile moving through my velocity at any radius. And so there does seem to be some relationship between density and the velocity at any radius. Of course, is it really density or is it something else? Because if you remember from our slice, my high density gas is sitting right here in the plane, and I'm moving to lower density gas as I move up in Z height in this selected region. So maybe it's not density, maybe it's actually the height along this cylinder. And so I can also do that. And I can say, okay, instead of looking at density, I want to look at the height from the center of the galaxy plane, which is that variable that I defined, Z disk. And again, I use weight-filled ones. And then I set my Z limit to -5 and 5. I don't know, it should have done that on its own. I'm not exactly sure why I required that. But you can play with that on your own to see if setting that makes a difference. And then, I don't know, this is taking a really long time. I feel like that is actually generally true of phase plot. It takes a little bit longer on my runs than slice plot or projection plot. Okay, so wow, this looks totally crazy. And the reason for that is because I was foolish and I didn't actually take the absolute magnitude of z disk, right? So I can see that this like yellow line is right next to a dark blue line, and yellow is up here at 5, and or purple is down here at -5. And so instead I gotta go back and add a new variable and say, okay, I actually want it to be the absolute value of z disk. And so then I do the same thing. And but while we're waiting for that, I'll point out this other thing. And I didn't have a great solution for this, and maybe other people can help me brainstorm what to do here. Because if you remember from up here, I have all of this gas here sitting at like 5 kiloparsecs, 2.5 or 250 kilometers per second, right? So I have gas here, but I can't see it because presumably it's right along, the plane of my disk. So z equals 0, which is why it's blue. But all of the gas that is not contained within my disk choose region, I think I selected disk choose here. Yeah, all of the gas which is not selected within my disk choose region is also being set to 0 in phase plot. And so I just have this blue bath of background. And so I'm kind of losing a lot of information there. And I didn't have a good solution for this particular phase plot to make this show up better. And I don't know, I was thinking, trying to think if I could set some histogram values to something slightly different. And you probably could do that in your settings. So if you dove into create profile again, okay, here's with my absolute value. And you can see a very nice relation there again between height and velocity. And so it might be more about height than about density. But again, we're stuck here because we know there's gas here from that density figure, but because everything is being set to 0, that's not in that's not in my region, I lose a lot of information when I have something that crosses 0 as my color axis. So that's something to think about. So I think you could possibly get away from it if you, okay, so here, kind of ignore this. So if I set everything, right? So if I had a histogram equal to, maybe I just type it out. Okay. So if instead of this, right? Let's see. Ooh, I feel like this is going to backfire. But okay, let's see. So let's not do that. Let's do disk choose. Let's do, yeah, that's right. And I want to do, what did I call it? ABZ disk. Very, very clever. Yeah. Okay. Weight field. Let's not do that. That's going to take a million years. Equals. Oops. 1. Then you might be able to get away from it because then I'd say, okay, gas. This C disk. And then I say, no, that's not going to work because I'm off 0. Yeah, I was hoping that I could come up with some clever way to say if abz disk equaled some number that was just a tiny smidge over 0, then I could pop it up, but I'd still lose all those exact zeros. So if this cell center is at exactly 0, then I'm toast. Oh, I could actually change this variable. Maybe that's what you do. Change this variable slightly so that you shift everything by a little bit, and then you can set everything. And then you can set the values, the histogram values off of 0. Did that make sense? No. So if instead of abz disk equaling, right, z minus 0.53, instead have it equal z minus 0.5. I don't know. This isn't my box, so I can't probably do this on the fly, but you do it like z minus 0.56. So now everything is shifted by 3 kiloparsecs. And then nothing should equal 0. It should be out of my box if it equals 0. And then I could probably get around it. Anyway, so that was just possibly useless fiddle. But then I'll just show you one last thing, which is the other great thing about using create profile is n-bins. So this is incredibly high resolution data, which I was excited about when I first started. But then when I tried to show this one thing that I often run into in my own code, it took me forever to find it. And so if you're going to do a profile, either 1D or 2D like this, where radius is one of your variables, you can end up running into cell size issues. And so here you have all of these kind of lines in radius, and so you can fix this by just carefully setting the number of bins that you have, so that you're falling so that every bin is making sure that it falls in a number of cells. But that's just something I've noticed in profiles. But you can see in this particular high-res run, I had to use a tiny radius and 1,000 bins, 1024 bins, in order for these lines to actually show up. So, as long as your data is high enough resolution, I guess you can get around it. So those were kind of all of the Phaseplot use cases that I could think of. Does anybody have any questions or things to add?
Definitely, I would say that was awesome.
Yeah, it was definitely awesome.
Okay, hopefully that was okay. Yeah, I don't have any insight into like the guts of YT, so I can't.
No, so here's the fun thing that you did without even knowing that you did it. You raised like 3 quirks along the way that we're going to use tomorrow in the demonstration of working on YT to help with issues and pull requests and all that bit.
Cool, good. Yeah, make Phaseplot even better. That's so good for me, because that is what I use constantly.
It's all thanks to your feedback. So now you're going to make it better, actually.
Yeah, that's awesome. That's so good.
All because of you.
I'm so stoked. Okay, but I feel like a lot of people might probably signed in because they wanted to volume render, which is actually my least, something that I use less. And of course, I left myself 14 minutes for it, so that's perfect, because I don't actually know very much about it. So yeah, but the great thing, before I attempt to kind of roll through at least some of this, let's see. The great thing about volume rendering is that there are so many web pages on ytprojects.org about volume rendering. So, you can find just about anything that you want to do there. And then you just get to fiddle, because if you're doing a volume rendering, whatever I tell you is something you're going to have to fiddle with to your own particular use case and your own taste, because you can just go totally nuts on volume rendering. But that said, let's rock and roll. Okay, so for this one, I'm going to go back to our isolated disk galaxy. So if you're using YT4 and you want to do load sample, do what? DS equals YT load sample. Is it called isolated galaxy? Something like that, right? Yeah, okay. So, okay, so let's take a look yet again to just a projection of the whole box. And the reason I'm using isolated galaxy is to kind of attempt to eliminate all of that really long wait time that we had on high res. So, oh, it tells me that you raised your hand. That's very cool. I don't know if that happened to other people sharing their screens. Anyway, oh, maybe because I'm host. In any case,
Yeah, I think because you're host.
Okay, that was so cool.
So just to understand, what's the 0030? Is that indexing into a snapshot or something?
Yeah. So, right. These are just the data dump file structure is. So this is Galaxy 0030 is kind of this folder where the 30th output is going. And then this is kind of the restart file with all of the information. And so there's also there's going to be different CPU files also kind of under this. But Galaxy 0030 will point you to all of those files.
Yeah, so it says so when you just do isolated galaxy, it defaults to load like the last snapshot or something?
Yes.
Is there a way to manually select a different snapshot then when I say load sample isolated galaxy?
Not with isolated galaxy because there's only one, but with Enzo Tiny
Okay.
Cosmology and so on, yes, you just supply a second argument.
Okay, cool. Thanks.
Cool. Great. Okay. So if we look at projection of the whole box, there it is, the wackadoo galaxy. But it's actually not that wacky. You know, we're being really mean to isolated galaxy, but it's pretty cool because it has this it looks like a CGM to me. So it has like a CGM and then this disk in the center. Okay, so I got to learn about volume rendering a little bit while I was trying to make this. So we can step through a couple things. So the first thing that you have to do if you're going to do any volume rendering is you have to create a scene. So the scene is a container class and it has information about both the source being rendered and the camera and the lens. And I didn't do anything with lenses. So you guys, that's an exercise for you later. And so if I create this scene using all of the data, then it tells me a little bit about my source. Okay, so it's telling me that the region's the whole thing, and it gives me my center in CGS units, and my left edge is 0, and my right edge is the whole size of the box because I didn't select any subregion. And then it tells me a little bit about my camera, its position, its focus, its north vector, the width of its field of view, and the resolution of my output. And then my lens, I've only ever used plain parallel lenses. Feel free to use perspective and other things. There's lots of walkthroughs about them. So, okay, so when I do that, my volume looks like this. And so you can kind of see where it's coming from. Here's a projection, and here is all these kind of fuzzy layers of different density gas. And so we can see what choices this actually makes for us by setting a few things and seeing what happens. So I'm setting the field to density, and I set log to true, and then I run it, and then we're going to see how similar it looks. Very similar. Okay, so it automatically selects density and it automatically selects things to go in log. Not that surprising. I feel like much of YT selections is like based on density and is on a log scale, right? Okay, so now let's try and zoom in. So here I'm setting some new data source, which is a sphere region, and it's centered on the center of the box, which is also the center of the galaxy, and it's 20 kiloparsecs in radius. And then I'm going to check out a slice plot of this data source. And I'm almost 100% sure that I could have typed data source in here, but just to be explicit, you can also just say data source equals whatever your region that you want to use is. Okay, and so when I do that, I'm seeing the entire box of my simulation because I didn't set a width to my slice plot. And I see my little tiny 20 kiloparsec region that I've selected. Fantastic. But that wasn't super helpful. So here I've got a projection plot where, again, I've got my same data source, same center, but I'm zooming in so that my width is 50 kiloparsecs, so I can kind of see what's going on here. And with my 50 kiloparsec width, my sphere of a radius 20 kiloparsecs fits nicely inside this projection. And so now I see I've got like this little disk here, which is very, those are happy galaxy guts. Okay, so, sorry, I scrolled a little too much. Okay, so let's zoom in on the volume render and do the same thing. So here I've created my scene in order to zoom in on a volume render. I think you actually could do some like zoom setting, but I like to be really specific and know exactly where the edges are of kind of what I'm looking at. And so I'm setting my width to 50 kiloparsecs. And again, density, log is true. Okay. So wait, and let's see. Also trying to watch the time a little bit. And I'm just gonna, there we go. Okay. All right. So now I've zoomed in and I still have these kind of density levels here. And you can start to get an inkling of that disk in the center. And so now another nice thing that volume rendering can do is it doesn't have to take, you know, your whole output. You can also use some region to make your scene and to create a volume rendering. And so when I do that, you can see it's very similar, but I've lost this outer region here because the gas that was right here is not actually contained in my 20 kiloparsec sphere. So, you know, so you will only get the region that you've selected from your data source. And okay, so this looks really crummy in my opinion. I can't really see anything. It doesn't look that beautiful. So, and I think that's because I haven't actually said anything. I haven't told YT, you know, what densities I want it to actually highlight in its volume render. And so you can go nuts on this, and I highly recommend that you do. I've put the link here, and so it'll be on the GitHub. So you can do this by manually setting the transfer function. And so what YT is doing is it's saying, all right, well, you want to be able to see through this, and you want to be able to see like different densities so that you get an idea of like the 3D shape of this. And so it just highlights different densities for you. And so I think the setting is here, your setting is kind of 10 kind of narrow Gaussians equally spaced in log space from the maximum to the minimum of whatever my variable is. But we can actually take a better look and say, okay, I'm just going to use this transfer function helper, and I'm going to say, okay, I want my transfer function to go somewhere between 10 to the minus 30 and 10 to the minus 23 in CGS density units. I'm going to call this transfer function helper. I'm looking at density. I'm setting log to true. I've set my boundary, and I'm going to just take a look at my transfer function. And I say I'm going to have my transfer function have 5 layers with a width of 0.05. So let's take a look at that. And okay, so this is showing me, I don't actually know. I guess I hadn't even noticed this. Why are there only 4 peaks in 5 layers?
There might be a very tiny layer at the far left,
That probably makes sense.
but
Very
maybe
tiny.
not.
Yeah, interesting. Okay. Oh, actually, we're going to be able to see that. Okay. And then, so what does this mean? So this is telling us the kind of the width of densities that are being highlighted in these different layers. So if I change that W from 0.05 to 0.01 and I run that, then you can see I have a much narrower range that's being highlighted. And so you can kind of get kind of a cleaner edge to your densities that are being highlighted. And then another thing that I highly recommend is you can actually take a look at the distribution of your gas across your region. And so this is looking at the gas distribution here. And so, yeah, my most dense region, or my most dense Gaussian, is highlighting my densest gas, but maybe these are highlighting densities that are interesting. Maybe they're highlighting densities that aren't interesting. And so you can kind of fiddle with that through this transfer function helper. So I'll leave that for the rest of you to try and play around with, because yeah. So we have 2 minutes, and also because I didn't do any more prep for it. So, okay. So now we can try and take a little bit more of a look at transfer function. And let's see, this is going to show us the scene. So here I've created a scene using all of my data. I've set my width to be 20 kiloparsecs. So I'm really looking at the central region, the guts of the galaxy. Density, I'm setting my bounds so that I'm only looking at kind of denser gas, 3 times 10 to the minus 27, 5 times 10 to the minus 24. And here you can set this thing called gray opacity. And if you set it to false, then underdense regions should be pretty see-through. And that's what this looks like with see-through underdense regions. And then we can take a look at what our transfer function looked like. If you notice, I saved it up here. And here's this setting. So I have a whole bunch of evenly spaced layers between my minimum and my maximum. And the brightest region in my volume render is the densest region. If I do exactly the same thing, but instead I set my gray opacity to true, this is supposed to make my underdense regions appear opaque. And so then I can run that, and we can see what that looks like. And we're about out of time. Well, we're 1 minute over now. So here, I'll show you the transfer function, then we can decide what we want to do here. Okay, so this looks totally different, and it could be cool for you, but it might not be showing what you want. And so now if we look at the transfer function, what's happened is now the brightness of all of my levels is the same. And so changing my gray opacity to true has just flattened this out, so that now I'm having a much harder time seeing through those lower density regions. And so I'm missing the dense gas in the center. So let me take a pause. I don't think we have anything else planned for this afternoon. So I'm happy to continue going through for it's probably about 15 more minutes. So it probably lasts until 3. but this also is going to get on the GitHub repository, so people can go through it at their own pace, at their own time, whenever they want. What do people kind of want to do? Should we do it?
Maybe
Oh.
people put their hands up if they want you to continue, and if we get enough hands up, we continue.
Sounds good. Someone else has to count. I don't know how many people are.
We've got
raising
one.
hands.
Anybody else? I'm putting my hand up. We've got 3, 5. I say we've got enough.
Okay, cool.
I say the show continues to be yours.
Okay, I will on with the show then. Yeah, and if people have other things to do, you are welcome to head off. This is all being recorded. And we'll go on the GitHub, so you don't even need the recording. Okay, so so those were a couple things that I noticed when you kind of let YT do whatever it wants with a volume render with some settings, but I never do that. When I use a volume render, I always tell YT exactly what densities I want it to highlight. And so that's what's going on here. So I've done the same thing. I'm creating a scene. I've got my same camera width, density, true, my bounds. I can't remember. I think they're slightly different than the other bounds, which was a little bit silly, but in any case, I've set my bounds. I'm creating this color transfer function so that I can directly sample a color map. And so for my transfer function, I sample this color map and I'm telling it at exactly what density I want. I'm setting the width of that Gaussian to be pretty narrow with that W parameter. I'm setting my alpha equal to 0.2, and we can look at that in a second. And I'm calling the Argray color map. Okay. So then I'm saying, okay, I'm setting my transfer function to be, right. I want to actually look at the transfer function helper. So I think that's why I called those things. And then I'm going to be able to take a look at my transfer function, and I'm going to then take a look at my scene. Okay. So let's see. I do that. Okay. Okay, so now here's my scene. And so with just those few layers, I now have an idea of kind of this, misty, lower density stuff surrounding this higher density disk. Maybe that's great for you, but it's always good to take a look at your transfer function. My transfer function tells me that I chose terribly with my densities to highlight. Like my highest density that I'm highlighting has no gas at it. So, maybe I should make some changes there. The other thing that you can notice is all of my Gaussians go to 1 except for this lowest density one, which, if you recall, I manually set alpha to 0.2. So I made it a little bit more see-through, and you can see that reflected in the transfer function. So if you wanted, you could make, that nice little set of 10 Gaussians you wanted manually. Okay, so let's change a few of our selections to actually get it to look a little bit nicer. I didn't like that highlighting of the low density stuff at 10 to the minus 26, so I'm getting rid of it. I'm keeping the other 3 layers, but I'm fixing my highest density layer so that it actually shows gas that's in the simulation, because, why not? Okay, so when I do that, what do I get? I think I get a little bit of a nicer one. Okay, now I'm really just kind of looking at this disk, and I actually can see some green. So I'm highlighting some of the highest density clouds in this disk, which is pretty nice. And when I check out my transfer function, oh, here it is. Yes, I can see my density, or my mass distribution across density. And yeah, I'm selecting a decent amount of gas at the densities that I want. Okay, great. So then just in here, you know, maybe you like this as dim as it is. Maybe it doesn't feel dim to you. But if you want to brighten it up, you can use this thing called Sigma Clip. And so instead of just SC all show empty brackets, I can do SC all show Sigma Clip equals 5. Comment that out. And when I run this, then I think it looks really cool. And you all can decide. And so what it's doing is it's getting rid of the super bright pixels so that the rest of it can really show up. So I like the look of this. I'm feeling pretty good. Okay. So, right. So you can also, I've just let the camera do whatever it wants in terms of viewing angle. And so you can set the viewing angle that you like. It is, you can go totally nuts on this. I often like just viewing along an axis. And so, you know, I'm going to try to get my volume render to look just like our, whoa, it's so far away. Okay, to look just like this projection. Okay, and that's actually pretty straightforward to do. So to do that, okay, I do a whole bunch of calls on my camera. So we've already seen camera calls. So camera set width, I can call a particular position. Here I want it, you know, right on 0.5 of X and Y, but in the Z direction at 0.95. I'm focusing on the center of the box. And then here's a new setting. So I've set the north vector of the camera to be at 0, 1, 0. And once you set a north vector is not a camera property. And so this is another thing that might be fun for us to attempt to do tomorrow when we're hacking. Because in order for the camera to actually read this new north vector, I have to call this camera switch orientation. Otherwise, it's not going to throw you an error. It's just not going to do anything. But since I've called switch orientation, now it's going to spin its camera around for me. And another thing that if you wanted, you could call, you could really jack up your resolution, which is what I do when I'm making movies for myself. And then I haven't changed my transfer function at all. I really like the look of my Sigma Clip equals 5. And oops. Oh yeah, no, that's right. I like the Sigma Clip equals 5 look. And so we can see how all this looked. Hooray! It looks totally like the projection. So I was pretty excited about that. Okay.
It's like a soap bubble.
Yeah, it's so cool. But you might notice a couple things. So we have like this kind of funky line here. You probably wouldn't notice these things actually. I wouldn't have noticed them if I hadn't like side by sided some stuff. Anyway, maybe you've got like a little artifact here. And so in ytproject.org, it said the low resolution on this simulation is giving me artifacts. Like, all right, well, let's check that out. So, okay, so if you have a low resolution simulation, then to avoid artifacts, you have to set this use ghost zone setting in order to make it look a little bit nicer. I have never used this setting, although I am going to try it now because my stuff is not all that high resolution throughout. Every other setting is exactly the same. And it does, in fact, take a little bit longer to use these ghost zones. And we can wait. Oh yeah, so the other thing I did, which we're gonna talk about in a second, is I was like, let's just set gray opacity equal to false and see what happens. we can check that out too. I'm gonna just run a couple of these so that we don't have to wait a million years. Yeah, so as you can see from us sitting here, using ghost zones on a ton of outputs may not be worth your while. Okay, so, wow, I totally lost those artifacts. So much better. Yeah, ghost zones forever. I don't know, but depending on your the resolution of your data and exactly what you're using this for, this could be an important setting, which actually I'd never seen it before until I really started digging with volume rendering, which is why I decided to point it out, although it was somewhere in the docs. So, and it does improve the look a little bit. Okay, so I set my gray opacity to false, which was supposed to make, did I write that down so that I would know? No, I can't remember. Gray opacity equals false is supposed to make it easier to see the inside or something like that, I think. It didn't make really any change. So then if I say, okay, well, let me set it to true and see what happens. This is supposed to make my underdense regions appear opaque. Well, we can see what that does to our rendering. Nothing, as far as I can tell. And then if I look at my transfer function, yeah, that's the same. So, so the lesson I learned from this is that you can't just use gray opacity if you're sampling your own color map. I've made all of these settings manually, and so this gray opacity call is not going to overwrite it. And so you have to actually think about exactly what calls you're making when you do it. And then the last thing that I wanted to do was annotate this figure, because as you might have saw, it's kind of annoying to have this nice visual here where it's like, okay, it's showing me something about density. What exactly is it highlighting for me? And then, I have this separate file with the transfer function. So instead we can annotate this figure, which has a lot of very similar calls, I think, to annotating anything else. So the only things that I've changed here is I got rid of this gray opacity call that was doing nothing. And then you can set annotate axes, and I was a little lazy on this. I'm not totally sure what exactly this is doing for me. Does anybody know off the top of their head what this color call is doing for me?
I think Mike wrote that.
I vaguely remember writing.
Yeah.
That.
Okay. Well, that's all right, because I put a link here to the volume rendering with annotation. So people,
Yeah.
Your assignment for this afternoon is read it, and you can figure that out. So funnily enough, I can't actually show the annotated version, but I can save it. So I've saved annotated. I've done sigma clip equals 5. I've put my text at this position, and I've put this text string that I defined up here, there. And so then I can maybe show it. Yay, and it looks so good. So here was all this text annotation. And here's my image. And here, so that your reader actually knows what's going on, you can see the transfer function on the side, which is lovely.
I think also if you turn on math text, the exponentials will be the exponents will really be exponents.
Oh, that'd be nice.
Yeah.
Okay. Yeah, so if I just did save annotated with sigma clip equals 5, then I wouldn't have this time output, but I would still have this nice transfer function on the side. The only thing I don't like about this, and I don't know, if it's what exactly is going on. But, I had this sigma clip equals 5 set so that it was like really nice and bright when we were looking at it, and it looked like so good. But then when I still have sigma clip equals 5, but this is really bright. My transfer function, it looks really bright on the screen, but this doesn't look so bright anymore. It like got all dim again. And I don't know why that happened. I don't know if anybody else has, a reason why that happened.
It might be because it's sigma clipping the entire image and not just the volume rendering portion.
Oh, yeah.
I see. Okay, well, maybe if I sigma clipped like,
Sigma
50
clips
or
a little bit of
something.
magic.
Yeah, I can see that. Okay, but anyway, and that way you can actually show everybody everything, which is of course what we want to do. Okay, so that's all that I had. Are there any questions for people about volume rendering?
I think you covered all the awesome stuff that I usually use.
Okay.
You mentioned lenses. And so people should check out some of the cool stuff about lenses, maybe.
Yeah.
Some people have done some awesome work on stereo, 3D.
Ooh. Does sound cool. Yeah.
So some of the other volume rendering programs I've used, like kind of need to be used interactively, like they need your computer to have a display environment and things like that. Is that the case here, or could you just run the same code on a cluster, like totally headless, and it would work?
Mm-hmm. That's what I do.
Oh, okay.
Yeah, that's what I do too.
Yeah. I know. Do you guys want to see my cool video that I made with volume
Yes.
rendering? Of course you do.
Yes, absolutely.
So this is, this is a little slow. So this is my galaxy that lives in a box, and I blow a wind through it rather than have it go through a cluster. And I've just highlighted 3 densities. And so I've been spending, I don't know, it feels like a lifetime identifying clumps in these regions across my tail. And at some point when I was like almost done with the work, someone was like, so are you sure that your density level that you like selected as your lowest density for your clumps is actually a good one? And I was like, well, I have no idea what good means. I looked at it. I feel like it's a number. And so anyway, but I was like, well, why don't I make a volume rendering where I'm highlighting that density and a couple other densities? And so kind of the red here is the lowest density where I've identified clumps. And here, if we play it, you can kind of see these, and they look pretty like individual little like loopy little clumps that are getting, they're kind of just like living throughout the disk. And this one's really cool actually, because you can see high density gas kind of throughout the disk. Even this whole box is like 80 kiloparsecs high. So this is like a really long tail of stripped gas that's like cooling into these pretty dense clumps. And so you can see the survival of these clumps. And then what's really fun is I have a whole bunch of different ones. And so this one is getting whomped by a wind that's 3 times as fast. So this was, a wimpy 1,000 kilometer per second wind. And this one is moving at 3,000 kilometers per second. And so it slams all the gas out. But actually, by looking at this volume rendering, you can see that like individual clouds are no longer these nice little beautiful little loopy things surviving, through the tail. They're just getting like completely shredded as they are getting stripped off the disk. And so I'm a believer that volume rendering is actually helpful for understanding the science going on in your simulation, which I was less of a believer before. It did make beautiful movies.